let's jump right into it and start looking at what's happening. So we'll start with a brief overview and then get into specific issues of how ice is melting, land ice is melting, and what contributions we expect to sea level rise, and so on. There is already very clear evidence that glaciers are melting, both over Antarctica and Greenland and many other sites around the globe. And there are differences in the processes, the drivers of these meltings, and the acceleration of melting. So if you start with the cumulative surface mass budgets of Greenland ice sheet over 2019 and 2020 and show other years like 2011, 2012 and 1981 to 2010, why do we do that? Basically, when you think about glaciers, they are several kilometers thick when they are in full blown state of being in a frozen state, not having melted since the last ice age. We are in a deglacial because the glacial extent, glacier volume over land and so on is much less than let's say 18,000 years ago when the last ice age started going away, right? But nonetheless we have these massive glaciers on Greenland and Antarctica, and they are melting because of global warming. So we have to understand how they are melting. So that means either tracking their mass budget, which is the idea of how much ablation is happening and how much accretion is happening. But there are other methods where just the height of the glacier is monitored using satellite altimeters that also measure, for example, sea level rise. And you can also track the sea level rise and estimate the contribution from glacier melt by separating it from the contribution from the so-called thermospheric sea level rise, which is just related to warming and other density changes like salinity change, for example, right? Excellent. So typically you look at it as a surface mass budget here, and this is the gray shading here is showing the mean over 1981 to 2020. So you can see that there is a large uncertainty or variance in these estimates, and you always look to see if individual years remain within that range that we have over these decades or they jump out of it, right? So if you look at 2019 and 2020, that is still there within the large uncertainty, but 2011, 2012 in terms of the melting, you can see the drop here in gigaton. So about 361 gigaton loss corresponds to 1 millimeter rise of sea level across the world. Okay, this is called eustatic sea level rise because when you melt glaciers, it's water that was taken out of the ocean and put on land and locked up. Now you're going to put it back into the ocean and it distributes over the whole ocean. Patterns are not constant. It's not like a bathtub because of dynamics, ocean currents, winds, etc. But nonetheless, the mean sea level rise of 1 millimeter occurs when you lose 361 gigatons of glacier. So this 2011-12 jumped out. The fact that 2019-2020 went back means that changes in the climate or ocean heating can still prevent glacier retreats and maybe even start to build them again. So there is a high frequency component to it as well, but we have to remember that if they are lost, then they are not going to recur in human timescales. Okay, we'll see those kinds of details. Here is a map and chart of Greenland ice mass changes from April 2002 to August 2019, and you can see that there is the mass change in gigatons again, and this is the equivalent sea level rise in millimeters. So that's the number I was mentioning. This is measured from a satellite called GRACE, Gravity Recovery and Climate Experiment, which has two satellites following each other at a certain distance, and when gravity of the Earth changes, there is a little pull and change in the orbit that is tracked very closely as the difference between them, which corresponds in some way to the mass changes. Could be because of groundwater extraction or could be because of glacier mass change. Okay, so that's how it is done. GRACE FO is GRACE Follow-On satellite mission. So I won't go into the details, but essentially you can see that where there is blue colors, there is a slight water equivalent gain or mass gain, and where it is red, especially on the edges here with some hot spots down here, there is ice loss. Ice glacier is losing mass. Obviously that's resulting in mass change, and you can see that sea level rise here, the scale is going downward, so sea level is actually increasing. Okay, this is the story. So obviously there is dynamics happening. There is a lot of loss just because of the winds blowing away snow and ablating ice, but there are also other processes which can either reduce mass loss or maybe slightly add mass at the top, which is still at high altitude, several kilometers, and still very cold, and still can hold ice and snow and grow the glacier. Whereas here, low latitudes and ocean warming and other factors begin to become very critical. Just to add a little bit of details on the Antarctic land ice changes in the same context, here again is the sea level contribution going positive down, and mass change, obviously gigatons of loss. These are different parts of Antarctica, the total West Antarctica, East Antarctica, and Antarctic Peninsula. You can see that there is large dynamic differences here as well, and we will see where that actually comes from. Antarctica is much more complicated because the Southern Ocean that surrounds it is very different than the ocean around Greenland. Okay, so that makes a difference, and Antarctic Peninsula is experiencing different climate impacts and ocean impacts compared to the east and west as well. Okay, so we'll look at many such processes. This is called a moulin, where the melting of glacier on top, for example, results in ponds of water where the reflectivity drops greatly. So snow and ice are very reflective, albedo we call it, which means water, which is the consequence of melting, also begins to absorb much more energy, and then you have the so-called ice albedo feedback, and then you can begin to create these rivers which then begin to drill into the glacier and can reach the bottom and also begin to lubricate the glacier from the bottom and create all kinds of processes. So firn is the falling ice that is still not frozen into a glacier, compressed into a glacier, and then you have the distribution or glacial movement. So this compressed ice is actually a compressed snow that becomes glacier, is like molasses, it flows. Unlike the frozen ice, which is brittle, this one flows. So you can see the process here. There is a GPS measurement here, and equilibrium line is basically where there is a balance of accumulation and loss on this side, and here there is a more ablation than accretion, so there is a loss. Okay, so this is how crevasses get filled and cracked. This is how moulins get formed and make it to the bottom and create lubrication against the bedrock and can accelerate glacier slide and glacier breakups and so on and so forth. So lots of processes and details that are region specific, but this is just an introduction, so we are not going to go into the complicated details, but there is lots of good literature that you can follow up on, especially papers by people like Rigno and books and reports and so on and so forth. Okay, we'll continue this story in the next podcast.